Welcome back, everyone. We are looking very much forward to a second exciting talk of Professor Kaplan. And for this talk, we thought it might be a nice idea to have one of his former students introduce him. And that is Amir Avishai, who did a PhD with Wayne. And so I give the floor to him to introduce this talk.
Thank you. Okay, so it's a great honor for me to get a chance to introduce my supervisor. I've known Wayne for a bit over 25 years, since he actually was a student like you guys, I guess, some of you. And I was an undergrad student, and I was his lab assistant for almost 3 years, doing TM samples for him under the supervision of Professor David Brandon. Since then, Wayne has become a role model, as my mentor and a role model for me, and I'll tell you why. You've heard yesterday a bit about his scientific and academic accomplishments. That's not what I'm going to be talking about today. It's going to be more of my personal experience as a student with Wayne. And as I said, it started first of all as...
I'm scared now.
No, I left out all the interesting parts. This I tell them in private. It started first of all by working with him. The chance of, as an undergrad, to work and try new things. He got to the point where he actually got me to get trained on a TM before I actually finished the undergrad degree, which was really exciting for me. And his curiosity, really working with him side by side with him, really got me so excited about the science, something that I really wanted to do. When I came as an undergrad, it was really dry lectures, and after being 3 years in the lab, there's no question that I want to do research. And he really helped me get into that. So that's something I'm really, really grateful for. Later on, when he came back as a PhD, as a faculty, and I started my PhD, I joined his group and discovered that the reputation he got was correct. It's not only that you had to work hard and late, he expected you're going to be accurate about your data, very clear, very critical about it. And when you come to ask him a question, we make fun of our Jewish people. You come, you ask one question, you get 2 questions back. So I never got an answer which was, that's what you need to do. He said he would ask me another question to lead me, and then give me another 2 papers and say, come back next week and give me an answer to your question. And it was a bit annoying sometimes to do the long way, but he really trained us to be independent researchers. And that's something that I use every day in everything I do today. I'm not scared to take something new. I'm not as courageous as he is, but hopefully getting close. And another thing I wanted to point out, if you noticed yesterday here, and you notice it as well today, this is Wayne. And this is another thing I love about Wayne. Everything is open. He shares. It's all about sharing the knowledge with everyone. And that's something, I don't know if I'm successful with you guys when I work with you, but I try. A lot of the things I tell to everyone when I meet you is what Wayne told me, is don't be scared. We're creative people. We can make more. Don't be afraid to share what you learned here. And that's what Wayne stands for me. I'm sorry. For me, it's...
Enough.
So I'll let him introduce the talk.
Thank you. I've never quite had an introduction like that. Let's go to science.
I confuse him a lot of times.
Yeah, this is perfectly. I feel quite at home with this. I'm going to start. Yesterday we had a bit of an introduction to wetting, partial wetting, and non-wetting. Today I'm gonna dive right into these interfacial states. What I called Bob yesterday, in order not to get Arthur angry. He's not here, so we'll continue calling them Bob, or complexions. And there's a list of people here. Yesterday was a tutorial. Today there's a bunch of people that have contributed to this, and they're listed. Actually, I put a mirror down. I'm not going to show any of your data from way back when, but a lot of the experiments that we went off and did afterwards were a result of the questions that rose with you during your work. Anyway, let's get to work. So we're going to talk about an interface. And when I put up an interface, we normally ask several fundamental questions. First of all, we talk about the structure. That's kind of automatic for the microscopist. The orientation, macroscopic degrees of freedom, microscopic degrees of freedom. the spectroscopists will automatically start talking about the chemistry at the interface, and I touched about that yesterday with equilibrium segregation or adsorption. And then there's, of course, the thermodynamics, and yesterday we talked about that as well. We talked about wetting and how we can work out these details. And of course, the end goal is to see if we can put these things together for this planar contact between two bulk phases. And I remind everyone that when I talk about an interface, that of course includes a free surface because there's no difference. So the outline of the talk today is I'll do some work on terminology, and then I promised you yesterday that I would try to prove to you experimentally that this concept of complexions is real. In other words, these first order transitions at an interface must result in the minimization of that interface energy. We need to prove that. That's not an easy statement. And then I'm going to go back in time and look at a completely different phenomena. On one hand, it looks different, and that's ordering at solid-liquid interfaces. Ordering the liquid. I'll show you that the liquid is well, it's not a liquid, and it's not a solid. It's something in between. And I will try to prove to you that there's no difference between that and what we call intergranular films. It's exactly the same phenomena. It's exactly adsorption. And then I'll end with two very simple examples of solid-solid interfaces. And I'll try to show you that we can also have complexions without any change in chemistry, just structure. So yesterday, I put up this concept of the Gibbs adsorption isotherm. And just to remind you, we talked about this reduction in interface energy because of a change in the chemical potential leading to the arrival of certain species to the surface. Okay? So atoms in solution will go to the surface if their presence at the surface reduces the surface energy. That is the driving force for segregation. And I'll say it again, it's not because the bulk is over the solubility limit and is going to do anything it can to throw that stuff out. That's not, that's enrichment, that's not segregation. And we looked at this hypothetical adsorption isotherm, where on the x-axis we have activity. On the y-axis, I put down yesterday number of atoms per nanometer squared, the amount of adsorbate. And as we increase the activity of a dopant, if the dopant's arrival at the surface reduces the surface energy, we'd expect to find more at the surface. And yesterday I showed the possible first order transitions. I've added here not just adsorbate, I've added here order. Now that's not in the Gibbs adsorption isotherm. Gibbs talked about the number of atoms per nanometer squared. Actually, Gibbs didn't even know about atoms. There weren't atoms back in Gibbs' time. I think Gibbs knew exactly what atoms were, but there was no Bragg. This is way before Bragg and these concepts of crystallography and structure, but the thermodynamics were clearly defined, but he didn't talk about the order. And I'll try to show you today that that's actually important and it has to be part of it. So in addition to this gradual increase, what I claimed yesterday was that we could have an instantaneous or discontinuous jump in the amount of adsorbate or a discontinuous change in the order at a surface if that minimizes the surface energy. So that's Gibbs. And just to remind everyone, we call this complexion, and this is based on, and I don't know if you've ever seen this, Roger, this statement here. And if you can't read it back there, from the diffuse interface model and wetting experiments by Carter and Cannon involving an excess of alcohol, the term complexion was derived. Craig likes that very much, and it's very accurate. And that's the concept of this word complexion. It just means the equilibrium state of a surface, minimum energy via balance of chemical and structural components, aspects. Let's call it aspects. Actually, there's a lot of experimental evidence that this exists, which has been accumulated over the years. Intergranular films is here. This phenomenon of this kind of film at a grain boundary in ceramics, that's probably the oldest example, I think. I'm not showing it, but there's examples for polymers. There's certainly examples on the surface of ice, thin films of H2O, not water, H2O on the surface of ice. This is a film at a grain boundary of tungsten from Jian Lu. This is something I'll show you in a few minutes, and also this at solid-liquid interfaces. These are all hints that this phenomena exists, but we actually need to prove this, that this is really an adsorption phenomena, and it's what I was talking about or hinting about yesterday. So just to remind everybody, yeah.
What was the film on the tungsten case?
Nickel, if I remember correctly, and that's from Jian Lu, who's out in San Diego now, and the reference is down here somewhere. Yeah, Gupta, Yun, Meyer, and Lu, and from Akta, and it's tungsten, either nickel or nickel and tungsten. I can't remember. I'm sorry. So this is the oldest one of the oldest I could find. This is in silicon nitride. This is where everything started. This is the ceramic that they wanted to turn into combustion engine material and didn't work so well because of this phenomena at grain boundaries. And people looked at this using, at the time, advanced electron microscopy and said, wow, we have an amorphous, actually it looks pretty disordered, doesn't it? And they called it amorphous, liquid, equilibrium wetting film. And this generated a slew of arguments. And we have to ask some fundamental questions about this phenomena. But before we ask the real questions, let's just talk about the characteristics that have been experimentally seen. First of all, unlike conventional films, which will always break up, we talked about that yesterday, these thin films are stable. People have heated them, cooled them, they don't break up, they remain, they don't de-wet, as I explained yesterday. Furthermore, the chemical composition along the grain boundary in the film is different from any of the bulk phases in the system. So schematically, here's a grain boundary with that film that I showed you a minute ago, and here at the triple junction there's a pocket, perhaps of glass, perhaps of a bulk crystal phase. The composition here and the composition here are different, and certainly that of the grains are different. So it's not chemically identical to any other bulk phase that's in the system. Furthermore, and this is the killer, the thickness is absolutely constant all along a particular grain boundary, interface, or surface. Constant thickness. And if you add more of this wetting phase at the triple junction, the films don't thicken. They stay the same. The only change in thickness will come if you change the chemistry itself. So if you add more of this orangey stuff, whatever is happening at the grain boundary doesn't change. All of these are characteristics not indicating the existence of a bulk phase along the grain boundary. And that's actually important. I think this was first done by David Clark, right? And you redrew it and explained it perhaps a little bit better. And the concept was, okay, why are these things forming? Well, the concept, let's do thermodynamically. It must be reducing the grain boundary energy or the surface energy. So here's a plot of grain boundary energy as a function of misorientation. This is a perfect single crystal, low angle grain boundaries, high angle grain boundaries, cusp at special high angle grain boundaries. And this dotted dashed line was supposed to show what happens when you have this intergranular film, this phenomena. In other words, the grain boundary is replaced by whatever this thing is in order to reduce the energy. It won't happen for low angle grain boundaries because it's not energetically favorable, and perhaps not for these special grain boundaries. And David Clark called this replacement of a grain boundary by two interfaces between the film and the crystals. And that should get us a little bit worried, because that immediately means that we're talking about two interfaces. We're talking about the concept of wetting. In other words, we're replacing the grain boundary by two solid-liquid interfaces, and I wrote liquid, but of course it could be a solid, is now wetting that grain boundary and replacing the boundary that used to exist. Now, that can happen. That certainly can happen. There's no reason why we can't have a wetting phase at a grain boundary, and we talked about that yesterday. But that doesn't fit with the characteristics that we've seen for these systems. On the other hand, yesterday we talked about partial wetting, and that's what I'm showing here. So here's our grain boundary, and here's our second phase, and it's partially wetting, so we have a dihedral angle. The grain boundary stays clean. That's a hypothetical example, which I doubt ever exists. But for here on the board, it's clean, and we know how to use these dihedral angles from yesterday to describe the relative interface energies of the system. By the way, this would be partial wetting, but Roland Cannon used to call this wet and this dry. And then the last example, he used to call this moist. And that was just a kind of a joke, but we shouldn't get confused. This is wetting, this is partial wetting. And the final example, which is adsorption, is of course non-wetting. It's not really dry, moist, it's non-wetting. And here, that phase is there, but constituent atoms from that second phase are moving into the grain boundary. That they're in blue. And they're changing the chemistry and or structure of the grain boundary in order to reduce that grain boundary energy. That's just Gibbs. That's adsorption. That's 180 years old. There's nothing new there. And it's exactly the isotherm that I showed you before, and that's the concept which I think is correct here. Okay? Now that means that, it doesn't mean that this graph isn't correct, it just means that this 2 gamma IGF is not correct. We're not replacing the grain boundary with 2 new solid liquid interfaces or something like that. We're just modifying the grain boundary in order to reduce the grain boundary energy. Craig and Roland and their students actually describe this analytically. And pictorially, we can describe this using the tools that we talked about yesterday. When we talked about Cahn's critical point wetting theory. Yesterday we said that in this imaginary immiscible system, partial immiscible system here in the middle, we would at a critical temperature go from partial wetting to wetting. Here the blue phase is only partially wetting this red box, and as I go above this critical temperature, suddenly it's completely wetting it. Now that was the state between 2 bulk phases. Adsorption is not the state between 2 bulk phases. Now we're talking about the state of a surface. It may divide 2 phases, but we're talking about the state of the surface itself. So what we've added here now is a hypothetical tie line, okay, which does not describe the state between 2 bulk phases, but describes one particular grain boundary in this solid solution off in the green area. To the left of this tie line, the red is in contact with the green. If I go to the right of it, the red's in contact with the green, but there's a little bit of blue stuff there because that blue stuff is reducing the grain boundary energy. So it's not bulk, whereas Jennifer, it's describing a surface, a tie line describing a surface. Okay? Now, if we were to move in concentration from the left to the right and cross that, what would we expect to see? Well, we'd expect to see what I showed you yesterday. We're moving from the left to the right. The amount of adsorbate and or order is slowly changing, but as we hit that tie line, there's a discontinuous jump. And that's what marks this first order transition. It doesn't have to be a first order transition. I'm talking about first order transitions. It doesn't have to be. Okay, all that's hand waving. I haven't proven anything, right? We don't believe this because that's a lot of, well, there's not a direct proof. So we need an experiment to convince ourselves. And this is a tough one, right? Because a lot of the times we started at grain boundaries. And the problem with grain boundaries in a single phase system is that they'll never be in equilibrium. And I won't convince you that this is a minimization of grain boundary energy, because if it's a single phase system, it's polycrystalline, we're never there. We reach minimum energy state when those crystals have grown and there's only one crystal left. So that's a problem. We can't do this in a single phase system at grain boundaries. So for our model experiment, we decided to look at the contact between 2 different materials. And we started actually with this guy here using nickel in contact with sapphire, or copper in contact with sapphire, under controlled conditions, including PO2. But people complained and kept saying, oh, this phenomenon is just oxidation. So eventually we changed to gold. This is after Amir. And we did these experiments as follows. We took a piece of sapphire and we put down droplets of anorthite glass. Actually, that's anorthite that you actually made. Yeah. Then we equilibrated it, and we had these small droplets. And then we put down a thin, continuous film of gold. And then we equilibrated it again. And of course, the thin, continuous film breaks up into individual particles. And now we have these particles, and we can do both microscopy and some interface thermodynamics from the same interfaces. That's the idea of this model experiment. By the way, it's anorthite because in polycrystalline alumina, calcium silicon forming anorthite is what, in dirty alumina, is what often is found at the triple junctions, and emanating from these triple junctions or these phenomena along the grain boundaries, and we assume that this is somehow associated with it. When we equilibrate, we get something that looks like this. These particles of gold. I hope you can see that I'm too close. I can't see anything. There's some droplets of anorthite glass. Some of these particles are sitting in the droplets. There should be some particles that are droplets without particles, and particles that look like they're in direct contact with the sapphire. When we lop one of these guys in half, using the fib, gold, sapphire, the glass, and all this is just deposition to protect the particle when we slice it using the fib. So there's some fundamental questions here about the intergranular film, that complexion, the structure itself. Is it really amorphous? They were used a lot, this term amorphous. It's a little bit difficult to talk about something amorphous or not when we're only talking 4, 5, 6 atoms across. One would expect some degree of order, yet the original microscopy didn't show that, or showed actually too much order. And of course, the thickness at equilibrium. And you can see from this data, this is from our aberration-corrected Titan, that there is indeed an intergranular film. This is the gold, this is the sapphire. There's no low-index orientation relationship in the existence of this phenomenon at the interface. If we take one of those particles, it's actually this guy sitting in this droplet, and section it. Now it's rotated 90 degrees to confuse us. The sapphire is on the left, the gold is on the right, and then from this phase of the exit wave reconstructed data, we can see the intergranular film itself, and I hope you can see that it seems to be partially ordered. If that doesn't convince you, we can overlap. Sorry, this is now the phase. That was the raw data. We can overlap the positions of the atoms. We can see the cations in this case. And there's a strong degree of ordering. Actually, you may argue that...
Are you sure this is not an artifact
like
of
steps?
Coherent illumination
So
leaching out into this region?
Okay, contrast delocalization?
Yeah.
Good question, contrast. Yes, okay. Well, contrast delocalization, it would be the killer here, and it always was the killer for these experiments. That's why these data is acquired with a very small value of CS. That's not enough. That's not enough.
See contrast?
This is exit wave reconstruction. The minute we've reconstructed successfully, we have 0 contrast delocalization left. So we've combined both the aberration corrected and exit wave reconstruction, okay? So yes, I'm convinced that this is not because of that. However, I can't, 1 minute, Peter, I can't prove to you that in the previous micrograph there might not have been a step in the depth. So we repeated this again and again and again. And this is probably the thinnest data set that we acquired. The phase on the left, the amplitude on the right. Let's zoom in on the phase for a moment. We can actually see the oxygen in this because of the reconstructed wave function. And here is the beginning of this film. And this is that ordering phenomena. We can actually see this using a type of Fourier transform and quantify it. So I'm absolutely convinced that this is real. But I'll come around and show you again a little bit later that it is.
So you have taken the factogram and...
No, we did do a Fourier transform of the wave function that we recovered. Not a Fourier transform of the image, which is, of course, not a diffraction pattern. And yes, we've extracted that, and we've actually extracted that at solid-liquid interfaces and found the exact same conclusions.
What's the chemistry?
Okay. Here it's really tough. It's not anorthite. It's a different silicon-calcium concentration. The actual numbers I don't even remember. We could never go beyond the silicon-calcium concentration. And even that ratio we extracted by extrapolating back to a 0 exposure, a 0 E-beam exposure. So lots of experiments where you go to a fresh area, acquire as a function of time, and then another fresh area as a function of time. These are a lot of work, and then extrapolate back to 0 exposure because we were concerned that we were changing it by looking at it. Steve Garofalini from Rutgers has been doing molecular dynamics simulations of glasses for many, many years. He did one of bulk anorthite and put it on our sapphire surface, and he gave us the positions of the atoms. We took those and made an exit wave and compared it to our experimental data. The experimental phase, reconstructed phase, is on the top. This is from Steve's data. For the microscopists, obviously what we did is we took the atomic positions, generated the wave function. From that, generated a simulated defocus series, took the simulated defocus series and went through the exit wave reconstruction to get back to the exit wave from the beginning, because that's the only kosher way to make the comparison between what we reconstruct experimentally, because there are artifacts from this code and the simulations. Steve saw or sees these silicon oxide cages with calcium cations at the inside, and this is what we think we see along the interface, so we had this type of ordering phenomena, and actually calcium at fairly specific. It's not crystalline, but it's not amorphous. It's partially ordered. Okay. Thickness. Also, that's important, and also a challenge. There have been a lot of arguments amongst microscopists about the right way to measure the thickness of such a film. And the biggest problem has been exactly what Frank said, contrast delocalization, Fresnel fringes at deep under focus, and this solves that problem, we think. So we measured, as a function of annealing time, the thickness from both the amplitude and from the phase. Let me plot this out, the results. What you see here is the thickness of this phenomena as a function of distance, this is in microns, from the nearest bulk droplet of anorthite glass. Let me redraw the schematically. So this guy was sitting in a droplet of anorthite glass. This guy was about 0.6 microns, 0.7 microns away, and this was over 2.5 microns away from the nearest bulk droplet of anorthite glass. These were annealed for just a few minutes at 1,100 degrees C. And what you see is that the film goes down in thickness as you move farther and farther away, indicating that there's still diffusion of the constituent atoms, and we haven't reached equilibrium. When we do it for 2 hours, which is really overkill actually, but 2 hours annealing, then the thickness is 1.2 nanometers, and it's absolutely constant. We saw no variance as a function of distance from the nearest droplet. So this convinced us that we had reached, I should technically not say equilibrium, it could be steady state. I could be stuck in a low energy configuration, but that's the best I could do. Heat that sucker up to 1,100 degrees C, and we waited for 2 hours and we didn't see any change in the thickness. By the way, that's the data that I showed you before from the microscopy from these types of experiments. By the way, there's another data point here, and this is on the surface of the basal plane of sapphire without gold. So schematically, we have a drop of anorthite glass, another droplet. Between these droplets, we cross-sectioned and found a film, as you know. And we explained it initially one way, and it has a thickness at equilibrium which is significantly different than what's here. And that makes sense because this is also 2 hours. That makes sense because it's a completely different animal. This is at a grain interface. This is at a free surface on sapphire. And actually, according to Amir, this should have even a different concentration than here, which is something that we never actually proved all the way. So if I just do some kind of intermediate summary, we did these model experiments. They're really simple experiments to try to separate out all these issues and convince ourselves that at equilibrium / steady state, this is constant. The thickness is indeed constant. We measured it, and these things are not amorphous. They are partially ordered. There's a degree of order in there, and that the chemistry is indeed different than what we saw before. But that's still not proof, because in order to really convince you, I have to show you that the energy goes down when this phenomena occurs. That's a tough one to do, which is why we invested a couple of years on this project going in the direction of wetting. So to remind you, we have this gold particle sitting in the sapphire. We want to know this interface energy. I yesterday explained to everybody that for solid-solid, we have this horrible problem of torque terms, which we can't ignore and can change the values, and the contact angles would not be valid way. We can do dihedral angle analysis if there are no torque terms. Fortunately for us, we have a bulk liquid here. So this is basically Young's equation over here. And then when we move our way around and down to the interface, we're actually moving at 90 degrees to every torque term that exists. So this is a fortuitous example because this glass is a liquid, and we can do it and extract an interface energy. So we started with the surface energy of gold, 1.4 joules per meter squared for the 111 surface. By the way, that's assuming that there's no silicon or calcium at that surface. That's probably not correct. So that energy is probably really lower in reality. We took the surface energy of the basal plane of sapphire, which we measured at 1.2 joules per meter squared. That's also assuming that it's clean and there's no surface silicon or calcium. But a minute ago, I explained that there is a film. So this value has got to be lower than this, but I don't know what it is, so I'll start with that. And that means that this is a conservative approach. Surface energy of anorthite is from a Cecil drop experiment. That's not a problem from the literature. And we measured the interface energy. It comes out to be 1.96 joules per meter squared. Using Winterbottom analysis, which I showed you yesterday, for nominally undoped pure gold on the same basal plane of sapphire, we measured 2.15 joules per meter squared. So there's a difference of almost 200 millijoules per meter squared going from the pure system to when we have an extra phase showing an adsorbate at that interface. That's a huge drop in energy, 200 millijoules per meter squared. That's not chopped liver. This is serious stuff. It's definitely larger than that because I remember I assumed the surface energy of sapphire and gold have not changed. They will be lower, and that means that this difference must be larger. So this is an underestimate of the reduction. But that's the best we could do. However, it convinced us that we do go down in interface energy. Okay? For those of you who are saying, wait a minute, aren't you above the solubility limit? Yes, I am. It doesn't bother us. It's the same type of analysis, but in a two-phase system instead of, three-phase system instead of what I showed you before. So actually, we do have this phenomena here, and these intergranular films, at least what I showed you at the gold sapphire interface based on anorthite, is exactly just adsorption. That's what they are. They're not amorphous, they're not wetting, it's actually dry, and it's just adsorption. Okay, let me go back a little bit and talk about what happens at solid-liquid interfaces. And I'm not going to go through the whole wetting story of this system, which we measured, but I want to show you just a snapshot from some data that we acquired at the ARM in Stuttgart. Really great high energy, high voltage microscope where we could do some heating experiments between sapphire and a droplet of liquid aluminium, and we did these at about 750 degrees C. And what you see here is contrast perturbations in the liquid adjacent to the solid. We had to work very hard to convince ourselves that these contrast perturbations are density perturbations. And we did that by two approaches. The second one was writing a partial exit wave reconstruction procedure. Partial because we could not acquire a series of function of defocus because of drift parallel to the electron beam. And the amount of contrast delocalization on the ARM was not insignificant, even though it was a lab 6. We spit blood over that. This is the analysis. What you see in blue is the partially reconstructed phase, and these are density perturbations out in the liquid. So what we have are layers of aluminium, where the aluminium atoms prefer to be in 2, 3, maybe a little bit more layers. And I won't prove this to you now, but within the first few layers, there's actually a type of planar heteroepitaxy, between the aluminium that's in these layers and the structure of the sapphire itself. Now, the ARM was really problematic. It was great to begin with, but it was problematic because of this contrast delocalization. So we repeated this on our Titan once we got it, and acquired many sets of data of these liquid droplets in contact with sapphire. And from where you're sitting, I hope you can see there's these contrast perturbations in the liquid. Now, even this is not enough, Frank, because while the CS is minimized here, and there's very little lateral drift, right? The electron beam's coming from above. There's obviously very little lateral drift. Doesn't mean there's no drift going this way. And you can't quantify that in situ. You have to do it offline. And that would mean an effective value of defocus. And that can cause significant contrast perturbations even at small values of CS.
I mean, you still always have an aperture that limits your frequency spectrum. And if you describe a sharp edge with a limited frequency spectrum, you get this overshooting. And you have to be sure that that's not what you see.
So we acquired this without an aperture, but that's not enough. We have to define the defocus value of a single frame and check frame by frame. This is what we did with the data from the ARM. It took us about 10 months per frame. When you have an aberration-corrected machine and maybe a little bit better code that we rewrote, it took us about 2 hours per frame. So what you see here is that interface, a frame, the liquid, the solid, the sapphire. This is simulated using this automated matching sequences, which we since then rewrote using a GUI for students because students cried when I made them learn how to do this themselves. Now we have an automated program which you can get from your own Kaufman. And we matched it, and once we match it, we know the value of defocus. And once we know the value of defocus, we know the worst case value of contrast delocalization. If the contrast perturbations go out further than that, it's real. If they go out less than that, we can't say anything. So we just went through data, and proved again and again and again, and then republished this as a small letter in PRL, proving that this data is real. Okay? So ordering in the solid, in the liquid adjacent to the solid is absolutely true. I can prove this another way, another experiment. And that's not using elastic scattering, but using inelastic scattering. This is Miri Gandman, Drozdov married Gandman. The concept is obvious. We all know these are bulk plasmons. Their energy has to depend on the density. And in the literature, people have measured this for solid aluminium as a function of temperature. And that's what you see here, the shift in the plasmon energy. We just went up in temperature to the liquid and looked at the plasmon. We had to use the plasmons because that's the only way we could get enough intensity out of the EELS spectrum to do something real. And we looked at the plasmon energy of bulk aluminium. So that's a continuation of the experiment that's in the literature. And this is the aluminium adjacent to the basal plane, adjacent to this rhombohedral plane, the -1014, and another plane. And actually, you can see it really does depend on the specific facet, which actually you would expect, because the order of the solid is imposing this ordering phenomenon in the liquid. Okay? So this is inelastic scattering. It doesn't have, well, it's not lacking delocalization, but we're not relying on that. This is a bulk plasmon, not an interface plasmon or a surface plasmon. So what I just showed you is, I call this ordering the liquid adjacent to the solid, but it's not really, it's not a solid, it's not a liquid, it's an adsorbate. It's not an adsorbate that is a change in chemistry, it's an adsorbate that's a change in order. Nominally, we haven't changed the chemistry there. You can call density of aluminium change a change in chemistry if you wish. It's equivalent, it's ordering, and that minimizes energy. Now, someone saying in the audience is saying, wait a minute, you've got this entropy term. Why in the world would the energy go down? And you're right, the entropy, there's a penalty to the god of entropy for this phenomena to happen. But if you want to think about it from the point of enthalpy, then these atoms in the liquid are sitting above the atoms in the solid, and they prefer to be at specific areas, specific bonding, charge transfer. And apparently that decrease in, we'll call it enthalpy for a moment, is more than the increase in entropy because of that ordering. Otherwise, it wouldn't happen. So I can be a little bit more quantitative about the entropy, but it's also a little bit of hand-waving and guesstimating. So in any case, I think that this showed that this phenomena is quite similar to what I showed you with the intergranular films. All right, let's leave that alone and go back to good old-fashioned solid-solid interfaces. We don't need these complications that we've shown you now for these films. And I want to show you two interfaces today. One is nickel on sapphire. We started looking at this simply because of the concept of adhesion between nickel-based alloys and alumina. Doing the model experiment that I described generally yesterday, we put these thin continuous films on the basal plane of sapphire in a furnace made of sapphire to keep things clean at a partial pressure of oxygen, which we measure and control, and we de-wet until we reach equilibrium in the solid state, not in the liquid state. Actually, this is just an SEM micrograph showing lots of large particles which are not at equilibrium, and I've circled little tiny ones which I showed you yesterday, and these actually had reached equilibrium. We saw them yesterday. This is the equilibrium crystal shape that we talked about. And I didn't show you yesterday the atom probe analysis that we did on these guys to look at possible contaminants. And we did experiments where we got it dirty and it changed this significantly. And we did experiments where we maintained as clean as we could. And that's from that we determined the surface equilibrium crystal shape and actually the surface energy of nickel. And we published that. But what we really were interested in is what's happening at the interface itself. So we go in, and as I said to you this morning, Peruz, this is nickel, FCC nickel on sapphire. This is as incoherent as we can get. There should be nothing really exciting here, but there was a PhD student, Hila Meltzman, who just didn't let go. And she kept looking at this and looking at this and looking at this. And this is the amplitude of the exit wave. By the way, I should point out I'm destroying this because Hila spent about 3 years on this, and I'm doing it in 2 minutes. But obviously, there's macroscopic degrees of freedom from electron diffraction. Then there's TEM from 2 different directions to determine the translation state of the particle on top of the sapphire. And then finally, the microscopic details of the structure of the interface itself. And what she noticed was this periodicity along the interface, and she solved this interface structure. Not the position of every bloody single atom, but the periodicity, the 2-dimensional periodicity. And it had reconstructed into a unit cell, which is 2.5 root 3 R30 by 2.5 root 3 R30. Now, I wanted to show you guys what that was yesterday, and I didn't. And I should have. And I'll stop now and just remind the students in the audience what reconstruction is. And this is on a surface. So this is just good old 111 surface of silicon that's been reconstructed and some beautiful STM data that I took out of the internet showing this 7x7 reconstruction. This terminology 7x7 comes from a way of showing the relative periodicity of the new reconstructed surface compared to the underlying bulk. Technically, there are a number of Bravais cells for a surface versus the 7 systems for the bulk. There are 5 for in the 2-dimensional. These are what they are usually called. And this notation of 2.5 root 3 R30, or the 7x7, is something that's called Wood's notation. And to do it very simply, imagine a surface where these are the gray atoms of this bulk. And we've replaced these atoms in a periodic fashion with these yellow guys, or removed them, it doesn't matter. Now, in this direction, the original A lattice, we have to go 3 lattice parameters until we reach the periodic unit cell. In perpendicular to that, we have to go 2 lattice cells. So this is 3 by 2 reconstruction with a rotation angle of 0, or a 3 by 2 reconstruction. This is this Wood's notation, and this is where all this stuff comes from. This cell that Hila found for the interface, not the free surface of sapphire in contact with nickel, this is the 1x1 surface of sapphire. The square, this guy up here, is this 2.5 root 3 R30. What does that mean? Well, actually, the basal plane of sapphire, let's ignore the nickel, reconstructs. It's been mapped out. There's the 1x1, and then as you hit There's some arguments about the exact reconstruction before 1150, but you hit the root 3 R30, the 2 root 3 R30, the 3 root 3 R30, and then the most famous root 31. That's probably the most studied structure. And there's the most atomistic data, because this is just the periodicity, of course. We reconstructed here in this temperature and got the 2.5 root 3 R30. This is the root 3 R30. For us, it's 2.5 because we don't have aluminium up here. We have nickel. It's an interface. It's on a free surface. But the symmetry is actually that of the sapphire. It seems to reconstruct according to what it wants, accommodating the fact that nickel is on the other side. This is an interface reconstruction. There's no difference between this and the 7x7 reconstruction of silicon. It's exactly the same phenomena, and they both happen to minimize surface energy. And the 7x7 is an adsorbate. It's a complexion. There's no difference between that, philosophically speaking, than anything else that I've showed you. No difference between this and the solid liquid interface or with the intergranular films. It's all just, I shouldn't say just, it's all wonderful Gibbs. One last quick example, which I have to show, and unfortunately Arthur didn't feel well and left, because this is the nickel zirconia. And we talked about the fuel cells. I learned about from you guys fuel cells this morning. We've been looking at this nickel zirconia interface using this de-wetting process. Again, looking at these tiny little crystals at equilibrium and doing microscopy and winter bottom analysis. So nickel on the 111 YSZ, the interface energy, absolute interface energy, is 1.8 joules per meter squared. And I can't remember the temperature. I think this is 1,200 degrees we equilibrated. There's a secondary low energy, low index orientation relationship, which is different than this one. This is the cube on cube orientation relationship. There's a type of twinned orientation relationship with the substrate, and the energy is significantly higher. We find this periodically, not very often, and we have an explanation as why that happens, and I'm not going to go into it right now. But we've done the energy, and I think that might be useful for some people. We've also looked at the translation at the interface and expecting to find an incoherent interface, just like I showed you for the nickel alumina, nickel sapphire. Albeit cube on cube, for this system, the mismatch is simply huge, okay? This is the twinned orientation, but of course it doesn't matter. We're talking about more than 30% mismatch for these two cubic structures. Should be incoherent. So what are these called, Frank, the name? We used to do this in the darkroom in Stuttgart, these micrographs where we inclined them.
Fume projection.
What he said. So we did this in the computer, of course, and the whole idea is just so that we can follow these planes along and see these misfit dislocations at this interface. Kind of surprised us, especially me, because I was hoping for this reconstruction. Actually, this is a reconstruction. Technically, it is reconstruction. Hadar actually solved the Burgess vector. It's the same for copper on MgO. It's been studied in depth to the past. Very similar. And there's one more data point that we were really curious, and that is the structure itself and the termination. For that, we turn to our new Titan in a box, this Themis, and it's both image and probe corrected. This is high-angle annular dark field. You were referring to this before. It's very nice, although the resolution is never as good as TM because of the distortions. I would move too if you shot 300,000 volts at me. But we can see the interface, and using this as a Z contrast, the intensity more or less to the power of Z to the power of 1.9. We also have an annular bright field detector. I don't like this technique so much. It has its problems, and you can see the variation in the image in the zirconia. But you can just smell these oxygen cations there. And I was pretty excited about it. I wasn't particularly happy. But FEI has this new quadrated annular detector from which they do something called differential integral phase contrast in STEM, which is basically the stuff that Yuichi and Shibata started, but looking at these differential between the quadrants of this annular dark field detector. For those of you who didn't follow what I just said, there's a paper, it's down below, and I can give you the citation, and it seems to really work. The most important thing here is that the intensity goes to the power of z to the power of 1, and not to the power of 1.9. So you can actually see the oxygen. You can really see it. Let me zoom this up so you can actually see it. And that is a column of oxygen, these guys. And this is the zirconium, and this is the nickel. And we can see that we got into a metal-terminated interface for this state at 10 to the minus 20 atmospheres of oxygen. So it's really not surprising.
Spend some time on tilting that specimen.
Untilting, yes.
On tilting, right? So that we get exactly what
Well, see, here I reminded everybody in the very first slide to whom this data belongs. And this is a low energy, low index orientation relationship. So we utilize that in order to, but you're right, there's a lot of very delicate work with Kikuchi and of course alignment to get to this. By the way, that's a fib specimen. So the bottom line is, even here when we have this massive mismatch, we have these misfit dislocations, which we talked about briefly this morning. And my best answer is that there's no difference between that and the reconstruction that I showed you for Sapphire. There are two different mechanisms to deal with this massive mismatch between these two lattices and to alleviate any elastic strain energy. One is reconstruction. The other is misfit dislocations, albeit at spacings which surprised me. The explanation which maybe helps to swallow this is to compare it to what happens at grain boundaries. So for grain boundaries, if we have a small angle grain boundary, we all know we have lattice dislocations which accommodate this misorientation. And from Reed-Shockley, we can estimate the energy and even estimate the distances between those dislocations. And as we go up, let's imagine that we were to change the misorientation angle between the grains, then that distance between the dislocations, of course, has to go down until we reach the field, the region of high angle grain boundaries, where there's no point to talk about individual dislocations anymore. And that's when all these theories about high angle grain boundaries start. And what we saw is that, we know that reconstruction happens here, although that word was never really used. For the interface, one can imagine an interface between two phases where you have almost perfect matching. Never exists, but let's imagine almost perfect. So a dislocation and then misfit dislocation, the next one's so far away I can't even see it. And now let's imagine that we can dial in the lattice parameter of one side and make it change until we get smaller and smaller spacing between dislocations to the point where we reconstruct. And that's what we understood we were seeing for the nickel on alumina, and it's been seen for copper on alumina as well. The nickel on zirconia kind of threw me for a moment, but basically I think it's more or less the same phenomenon. Why did I bring this last example up? This is a complexion. This is adsorbate. There's no chemical change. It's not the arrival of atoms. It's the reordering of the atoms to minimize the interface energy. There's no difference between what I showed you before in the two previous examples. Obviously, a change in structure, a reconstruction in the surface, by definition, is a first-order transition. Change in chemistry, not necessarily so. Here you have to do some work to prove that, but structure must be a first-order transition. Again, to remind everyone, because this has been misstated in the past, there are no limits to the number of complexions for a system. People write 6 for some reason, and that's nonsense. There can be 1, there can be 17. It's going to depend on the system, and it depends on, in an analogous way, to how many bulk phases can exist for a system. There's lots of open questions. I'm ending now. I've listed them here. There's lots of room to work. I think one of the more exciting things is the concept of triple lines and adsorption to triple lines, an analogy to absorption to surfaces. Actually, Craig Carter and I postulated this in a short paper, 4 questions about triple lines, which we wrote on Passover. And more recently, there was a paper by Dirk Rabe and his group that looked at adsorbates to dislocation cores. And they almost proved that there's a first order transition along the dislocation core. And hypothetically, I think that should exist. This little movie back here that's running is a case where we had liquid aluminum in contact with a sapphire, but we had a higher partial pressure of oxygen in our microscope, and oxygen was absorbing as well. And it's absorbing into these steps which sweep across the surface and are the mechanism for crystal growth. It's not just the steps, it's the steps interacting with this ordered regime which defines the way the crystal grows. If I confuse you with this issue of complexions, then 3 good friends of mine and I wrote this paper which we had the audacity to call the Rosetta Stone of wetting. That was a running title, never intended to publish, but the editor of the journal really liked it. So we decided to run with it. And actually, it was reviewed by graduate students because we wrote this for graduate students. And if I confused you, or if you want to expand on it, I'm quite proud of this, and I think it might be of some use. So with that, I'll stop, and I thank you for your attention.
Thank you so much, Wayne, for another great presentation with exciting results out of the world of interfaces and atomic resolution microscopy.
Yes. And thermodynamics.
And thermodynamics. Cutting edge work. The floor is open to discussion. I see Gerhard and then Roger.
You said that in some cases your situation is not in equilibrium, and that you have others that are in equilibrium. And your last movie was an example of not being in equilibrium.
Yeah. Well, it's growth, so.
So how do you define wetting something is in equilibrium? Is it based on the state within 1 second, within time? What is?
You know, as an experimentalist, I really can't tell you that. I can only say when it's not in equilibrium, right? I can say that a moving grain boundary, these are transitory states. And as it moves, its structure and chemistry certainly can disrupt and then return and change. And so I can't really make any positive statements about a moving grain boundary.
Momentarily, it should be in equilibrium too.
I don't know how to prove that to you.
Otherwise, you'll move away.
It's a point of argument which I don't have an answer for. Maybe somebody else does. I don't know how to convince you that any energy measurements I make from a grain boundary in a single phase system represents an equilibrium. Maybe a steady state, but I don't know how to say equilibrium. That's the fundamental problem behind it. It doesn't really have to worry us. If there's an adsorption phenomena in a single phase system to the grain boundaries, it's still only happening in order to reduce the grain boundary energy. It's just that the amount there and the total reduction may be different if we were at true equilibrium than when we were at a steady state. The driving force has to be the same. The end result, of course, doesn't necessarily have to be the same if you're not at equilibrium. I don't know how to escape that in any other way.
So, Wayne, with all of your examples, it's like a tremendous bestiary of all the things nature chooses to do. Right?
Yeah.
So it's like a little dictionary, we can look everything up.
Right.
And you say that it's all from Gibbs. And so now, you're an experimentalist.
Yeah.
But if instead we go and say, well, we've got this materials genome effort,
Mhm.
people are simulating all kinds of things and calculating all kinds of things. And yet, so why haven't the computational people just outrun experiment and showing us all the real behaviors to see?
Well, first of all, there's no reason that this couldn't be, I mean, we've built up phase diagrams. Why can't we add tie lines to describe, well, maybe not grain boundaries, that's a little bit presumptuous that we could do such a huge job, but let's talk about specific interfaces for a system as a function of thermodynamic parameters. Matter of fact, let's do that for systems which we would really, really care about. Not because they're model experiments that Wayne wants to muck with, but they have mechanical engineering properties which we would be interested in. In other words, let's say thin dielectric layers for microelectronics. That's where we should be mapping this out, because those thicknesses are not set by Intel, they're set by somebody else. And I think that's really important. As far as the simulations, actually, ordering at solid liquid interfaces we played with well before we did these in situ experiments. We could smell it from our wetting experiments, and that's why we went and did MD. But of course, that doesn't convince anybody. You have to do the experiments to convince. I think if for the other direction, like what Steve Garofalini has been doing for a long time, is shown again and again that this is part of the nature of the surface. What's missing is the adsorption isotherm. That's what's missing, both experimentally and computationally. And I'm trying to do it experimentally. Actually, the nickel that I showed you on zirconia, that's being doped with chromium right now to different levels. And we're measuring how much is in the bulk, and we're measuring how much is at the interface. And of course, we're measuring the interface energy and trying to do the structure as well as not just the chemistry, in order to try to map out such an isotherm. It's a lot of tedious work. It's pretty cool. It's pretty exciting, but that's what has to be done in order to do some engineering with this. In the long run, it's going to be faster to simulate it and then try to prove it here and there with selected samples. But I think that's comparable to CalFAD for complicated phase diagrams, and then select model experiments to confirm the CalFAD calculations.
John.
Yeah, I was interested in the liquid-solid interactions for a different reason. In some cases, you can use the liquid-solid interaction to improve things, and in other cases, it can be severely embrittling. So in one case, for example, if you have like a pre-machining alloy, you have a low melting point metal that's purposely put in there to help the machining. It melts, and then the machining is easy. But on the other end, you can have other liquid species that will severely embrittle a solid, like liquid metal embrittlement. And so I'm wondering if you could do a liquid on a solid in those kind of systems and look at what's really happening at those interfaces. Mm-hmm. Because it happens very quickly, but I don't think anybody knows what's really going on.
Whoa.
That's all of the interface. But maybe you've done.
No. There's just a massive argument about embrittlement at grain boundaries because of this phenomenon. And Mike Finnis has one very specific approach based on calculations. There have been wonderful studies done in Stuttgart. Wilfried Siegel, I think, did the best STEM work that I've ever seen of gallium at grain boundaries in aluminium. Definitely embrittlement, you see that, but he went in and did STEM work.
Bismuth and copper.
And bismuth and copper as well. And they're not liquids. It's adsorbates. Okay? So that, at those grain boundaries, are adsorbates. That's not a liquid. So it's a different phenomenon than what you were referring to in general, but definitely important.
Before we have Alf's question, I want to make a comment. It did not surprise me at all that the presence of a crystal templates some structure into the liquid or an amorphous phase. Mm-hmm. Because after all, we are looking at Coulomb fields, yes, which have infinite reach, mm-hmm, at least in principle.
Well, significant reach.
Well, if you look at the Coulomb law, you look at a free charge, yeah, electric field goes out to infinity, and in principle. And this is actually a phenomenon that is much broader. It is also true for solid-solid interfaces, where you have these misfit dislocations and their strain fields, and these strain fields reach out to infinity, so they impact the structure at any distance away from the interface, whether measurable or not. And it's also true for free surfaces that reconstruct. There's actually some lovely work by Laurie Marks, he presented, yes, this here about a decade ago, yeah, where you can also show by TEM techniques that he has developed that the surface reconstruction is not just at the surface, but the strain that it generates reaches out and actually impacts measurably
Down in.
a thicker slice below the surface. So that's actually a very general phenomenon of which you've shown an important aspect here.
So let me answer the Laurie Marks argument.
Yep.
If you take a TM specimen, let's imagine that it looks like this. This is the hole. The electrons come this way. We look in that thin region. If you were to heat that up just enough to try to equilibrate it, but not too much that it would, surface energy would make it ball up into a huge ball that would be too thick, then you would expect to get something that would look like this, best as I can do drawing. And now you have a free surface, which you can look at in cross-section. And if you have aberration corrected system, then you can look at exactly what you're saying.
I'll draw a vacuum microscope.
Yeah, but of course you can do it in oxide, and then you can do it ex situ.
Okay.
In any case, this goes down, we've seen in strontium titanate 6 atomic layers down into the bulk before you look at something that's not reconstructed anymore. So I absolutely, not measurably. So I absolutely agree with you that that's important. Actually, people argued about the solid-liquid ordering phenomenon for a long time. We just proved it experimentally and tried to associate it with this intergranular films, which I think is correct.
Help.
So when you put nickel on the sapphire, the nickel did not change how the structures reconstructed, just changed the parameters.
Actually, there was I don't know how to separate them because it's an interface. That 2.5 root 3 R30 includes both the sapphire and the nickel, the first layer of nickel. Now we looked carefully from there on into the nickel. There's a relaxation, change in lattice with no change in symmetry in the nickel side, which we could measure.
So if you made nickel smaller and smaller, thinner and thinner, how would you expect to change? And if I can then put, let's say, sapphire on the other side, onto nickel, would you expect the same type of reconstruction on the other end if I do a superlative process?
I don't know. I never thought of it that way. If you were to take off all the nickel except for one layer of nickel atoms, so you have no bulk, then that would be like as if you had nickel adsorption on the sapphire.
That is not nickel.
It's not nickel.
An electronic structure.
I agree, but that's the question. Then it's almost as if you had that root 3 R30, 3 root 3 R30 instead of the 2.5. Maybe because in the 2.5 you have it's just the in the 3 root 3 R30 it's an aluminium terminated reconstruction. So maybe that would be even different than the 2.5 versus the 3. I don't know.
And if I can, like you said, it goes slowly, like when we talk about the SQ, it goes 5, 6 layers.
Yeah.
Right? So would that be expected on the nickel side? And so it doesn't need to be one atomic layer, but if you could, a few atomic layers, and then onto that, if you build sapphire.
Well, I think we'll find that. I think we'll find that if you look on metals, that we'll find that the depth of the reconstruction is less than on more rigid ionic materials or covalent materials.
There are cases where you can template a different structure into a metal by interfaces. Like you can get body-centered cubic copper if you epitaxially grow it on iron. So something could happen here of that sort. That you see the nickel in a new crystal structure.
Okay. So, two unrelated questions. In your first movie, was that sapphire sublimating underneath there? So that's at 750 degrees.
Yeah, but we're shooting it with 300,000 volts. It's not just heating. We're also shooting it with electrons. Sublimating is not really a fair word. Knock-on damage is the correct term. And actually, that's how we make the aluminium. We didn't put droplets of aluminium. We took a TM specimen, which is thin, and you preferentially knock off is the more correct way of saying it, but in the literature it's knock on. You preferentially knock on the oxygen, and the aluminium balls up.
And it does de-wet the alumina as it.
You have a contact angle of about 84 degrees.
My second question is, when you had the two drops of the glass that has the same composition as anorthite, in the middle between the two, you had a measurable thickness of glass. So why,
Not glass, an absorbing.
Absorbing. But why do you retain droplets in that case?
Oh, it's
It is spread out if the absorbing.
oh, because it's a partial wetting. The anorthite has a finite contact angle on the sapphire, okay, and it doesn't want to spread. We haven't reached the critical point for wetting for that system.
So you will get the absorbate that is leaching material out of the droplet, and yet the droplet remains only partially.
Sure.
That's
Because the droplet doesn't want to cover the entire surface because that would increase the energy, because that interface energy is not all that low. But select constituent atoms from the bulk can go to that exposed free surface if it reduces the surface energy. So you have adsorption and partial wetting happening at the same time.
So presumably they're different compositions, right? The
Yeah.
absorbate is a different.
Absolutely.
Calcium rich there.
Yeah.
I thought you sold it by now.
We explained that originally looking at Hammacher coefficients as a function of calcium concentration. I don't know if I ever showed this to you, but we wrote this up that actually Mike Finnis had a proposal once that were not space charges, image charges on the metals, in the metal, which were orienting and defining the drop in interface energy of such systems, and not DLVO. For this system, we had absolute values, and we could actually measure that. And for this metal-ceramic interface, Mike was right. It's not that there isn't a portion of the thermodynamic work of adhesion that comes from DLVO type of surface forces. It's there. It's just very, very small compared to the image forces. But that's at a metal-ceramic interface, not at a general grain boundary, and that may be different. So now we're already arguing about very specific details. So.
I'm not sure. Dave, did you have a question?
Well, just following up on this ordering in the liquid that you've seen, I mean, the solidification studies, particularly the Japanese done using neutron diffraction, shows in the liquid side of the temperature isotherm, just as it gets close, that ordering starts up in the liquid.
Mm-hmm.
They sometimes call that clustering. I'm not sure whether that's a misinterpretation of Japanese word. And it shows up in the macroscopic properties of the viscosity. As you get closer to the viscosity turns up right before the isotherm. So the question I had was, do you think there's a, lack of a better term, an extra energy term because of the template that it's sitting on? Because in the homogeneous solidification it orders. Is there more ordering because of that?
Excellent, excellent. Really good questions. First of all, let's add to that, Mark Asta and his colleagues have done a lot of simulations at solidification fronts, and all of it showing this type of phenomena. But what I showed is at an interface between two bulk phases. One is a liquid, one is a solid of two different materials. So it wasn't really a solidification front, except for that movie that I showed in the end. So it's a little bit more static compared to solidification phenomena, which is a snapshot right in between this transient period. But as I said, I know that this entropy term can really drive some people crazy. I think if you look at this particular example atomistically, at least me, it makes me feel much better. It's clear that that first layer in the liquid or in the gas, those atoms are they'll have preferred sites over the solid. And that's charge transfer. That's bonding of one sort or another. And that's already a layer and ordering. The next layer is then influenced by that first layer. You'd expect the in-plane ordering to be different as you go into the liquid, and simulations, our simulations have shown that. But those specific charge transfer is, if you would, if you will, the enthalpy. And then you lose energy because of the order itself, and that's the entropy term. And as I said, if the entropy was dominant, this wouldn't be happening. By the way, Dave Slorovitz, when I first did these simulations the first time, said, Wayne, you're always going to get this phenomena. It's a hard wall phenomena in the liquid, and that's the way it goes. And so we went back and we redid our MD simulations, and I took a liquid and I froze it. So it's a disordered substrate, okay? No periodicity. Basically, we melted, this is with Adham, we melted some liquid and we froze it, and we didn't let those atoms move. Now we put a liquid of a different material on top of it and let it cook, reach equilibrium. With substrates perfectly flat, but disordered. We didn't see any ordering. Nothing. Not even that layering phenomena, really. So it's not just a hard wall calculation, the phenomena. It's real. It's real.
Let's take one last question by Pirous.
This reminded me also of some work about 25 years ago on amorphous silicon and silicon. And that was a lot of interest in Bell Labs, when Bell Lab was still going on. And there was this guy, Abosuna, and he was doing a lot of high resolution. And he took a lot of D-factor, which is the Fourier transform the intensity, unlike the diffraction pattern, which is the wave function. A lot of D-factor and going away, and there was some sort of ordering until a certain distance away from it, and then it came out of this. So this reminds me of
that data.
that thing eventually died. There was a lot of controversy. People didn't believe it. He was shouting more or less these things.
Well, thankfully, nobody's really shouted at me too much here. Maybe once or twice Arthur shouted at me.
We'll wait till the talk tomorrow, of course.
Yeah, tomorrow Arthur will shout at me for sure.
Okay. Let's give Wayne another hand for his